Hello, everyone. My name is Yanzhe, and today I'm excited to present to you our group's exploration of application of linear system in science and engineering. Linear systems are a fundamental tool in mathematics and engineering, enabling us to model, analyze, and solve complex real-world problems across various fields. In our presentation, we'll cover three key areas where linear systems play a crucial role. We'll begin by discussing how linear systems are used to analyze electrical circuits, where the relationships between voltage, current, and impedance can be modeled as linear equations. Next, we'll move to mechanical systems, where linear algebra helps us simplify and solve problems related to forces, displacements, and vibrations. Finally, we'll explore how linearization techniques are applied in fluid mechanics, particularly in analyzing small disturbances and simplifying the nonlinear behavior of fluid flows. Throughout the presentation, we'll demonstrate how linear systems provide powerful methods for solving complex engineering challenges. We hope that by the end, you will gain a better appreciation of how this fundamental mathematics concept is applied in various scientific and engineering fields. Thank you, and let's dive right into the first topic: linear systems in circuit analysis. In DC circuits, the relationship between voltage and current is simple and straightforward. According to Ohm's law, we have the equation V equals to I times R, where voltage is directly proportional to the current, and the resistance R is constant. But when we switch to AC circuits, things become a little more complicated. Instead of a constant voltage, AC involves a voltage that alternates over time, and the components in the circuit, such as resistors, capacitors, and inductors, all react to this changing voltage differently. This creates a more complex relationship between voltage and current. To understand this relationship, we introduce the concept of impedance. The impedance is like the resistance in an AC circuit, but it also accounts for the effects of inductance and capacitance, which don't exist in DC circuits. Impedance is a complex quantity and is represented as Z equals to R plus J times X. So, impedance combines both real resistance R and imaginary reactance X to give us a full picture of how the circuit behaves in AC. Now, you might think that because we are using complex numbers, the relationship between voltage and current is no longer simple. But that's not true. The relationship between voltage and current in AC circuits is still linear, even though impedance is complex and voltage and current remains linearly related. Just like Ohm's law in DC circuits, the key difference is that instead of using just a resistance R, we use the full impedance Z. So, in AC circuits, the voltage and current are related through the equation V equals to I times Z, where Z is impedance. This means that even though we are dealing with complex numbers, the relationship is still linear. We just need to use the complex impedance to account for both resistance and reactance in the circuit. Let's consider a simple RLC series circuit consisting of a resistor, an inductor, and a capacitor. The total impedance Z is the combination of resistance R and the reactance of the inductor and capacitor. Z equals to R plus J times the quantity X sub L minus X sub Z. As the frequency of the AC signal changes, the reactance changes, which affects the impedance. This causes the current to vary with frequency. Despite using complex impedance, the relationship between voltage and current remains linear as impedance links them. To sum up, in AC circuits, even though the relationship between voltage and current involves complex numbers due to impedance, it remains linear. The impedance Z equals to R plus J times X allows us to consider both the resistance and the frequency-dependent reactance in a circuit. So, when we use more complex math, the fundamental relationship between voltage and current in AC circuits is still linear, just a bit more detailed, but by using impedance, we can fully describe and solve AC circuit problems.
I'm Lin Jiacheng. Today I will be discussing linear analysis in mechanical systems, with a particular focus on the role of linear algebra in understanding and solving real-world engineering problems. Linear analysis is a powerful tool used to model and analyze systems where the relationship between force, displacement, and other variables can be approximated as linear. In mechanical systems, many physical phenomena such as vibrations, structural deformations, and dynamic response can be simplified using linear models. These models are based on the assumption that the system behaves proportionally, meaning the output, such as displacement or force, is directly proportional to the input. A key requirement here is that the system obeys the principle of superposition, which means that the response to multiple forces acting on the system is simply the sum of responses to each individual force. For example, when analyzing a spring-mass system, we assume that the force exerted by the spring is proportional to the displacement in accordance with Hooke's rule, F equals K times X, where F is the force, K is spring constant, and X is displacement. This simple relationship forms the foundation for more complex systems that can be analyzed using linear equations. Now, this is where linear algebra comes into play. Linear algebra provides the mathematical framework to handle systems of linear equations, which are crucial for analyzing mechanical systems. Mechanical systems often involve multiple interconnected components, such as springs, masses, dampers, and other structural elements, which together forms a system of equations that must be solved simultaneously. Consider, for example, a multi-degree of freedom systems where multiple masses are connected through springs dampers. To find the displacement of each mass in response to external forces, we can express the systems of forces and displacements such as a set of linear equations. These equations are often represented in matrix form. Ku equal to F, where K is the stiffness matrix, representing the stiffness of each component in the systems. U is the displacement vector, which contains the displacement of each mass. F is the force vector, representing the applied to external force. Using the techniques from linear algebra such as matrix equations, Gaussian elimination, or eigenvalue analysis, we can solve for the displacement vector U, giving us the system's response. In dynamic analysis, one of the most important applications of linear algebra is eigenvalue analysis. For systems involving vibrations, we need to determine the natural frequencies and mode shapes of the system. This can be done by solving eigenvalue problem, where the system's dynamic behaviors is covered by the equation bracket k minus the power of 2 of omega times m times u equal to 0. Here, k is the stiffness matrix, m is the mass matrix, and omega is the angular frequency of vibration. By solving these equations, we can find the eigenvalues and eigenvectors, which tell us the system's natural frequencies and how it vibrates at Rosse frequencies. This process is a direct application of linear algebra, where the eigenvalues correspond to the square of the natural frequencies, and the eigenvectors describes the mode shapes. To summarize, the linear analysis in mechanical systems help us model and solve complex problems involving forces, displacements, and vibrations all through the lens of linear algebra. By representing these systems as sets of linear equations, we can apply powerful linear algebra techniques to find solutions efficiently. Whether you are analyzing vibrations, structural deformations, or multi-body dynamics, linear algebra remains a cornerstone of modern mechanical engineering analysis. This script introduces linear analysis, highlights the role of linear algebra in solving mechanical systems problems, and emphasize key applications such as matrix equation and eigenvalue analysis in vibrations analysis. It provides a clear, concise overview while giving a focus on how linear algebra is used in engineering practice. Yeah, that's all. Thank you.
Hello, I'm Haocong. Today I will be talking about linearization in fluid mechanics, which is an important concept used to simplify complex nonlinear fluid flows equations for easier analysis and problem solving. Linearization involves approximating nonlinear relationships by linear ones, making them more manageable without losing critical information about the system's behavior. Why linearization is important? Fluid dynamics is governed by the Navier-Stokes equations, which describes the motion of fluid substance. These equations, so powerful, are highly nonlinear and can be difficult to solve directly, especially for turbulent fluids or complex geometries. In many cases, we can approximate the behavior of fluids under certain conditions by linearizing these equations. This process enables us to use linear methods which are easier to handle mathematically and computationally. Linearization is particularly useful when dealing with small perturbations in a fluid system, where the changes are small enough that we can approximate nonlinear terms as linear. How linearization works? Linearization involves approximating nonlinear functions by their first-order Taylor series expansion. Mathematically, for function f of x, we can approximate it near a point x sub 0 as f of x is approximately f of x sub 0 plus f prime of x sub 0 times x minus x sub 0. In fluid mechanics, we often deal with velocity fields, pressures, and other variables that depend on spatial and temporal coordinates. When the deviations from an equilibrium state are small, we assume that the fluid quantities can be expressed as small perturbations around the base state. For example, consider the velocity of the fluid. V of x and t equals to v plus delta v of x and t, where v is the base fluid constant velocity or steady-state velocity. Delta V of x and t represents the small perturbation. By substituting this approximation into the governing equations, we can linearize the equations and work with these perturbations terms only. Applications of linearizations is in fluid machinetics. One of the key applications of linearization in fluid machinetics is the study of small disturbance in a steady fluid, such as sound waves or stability analysis of fluid flows. By linearizing the Navier-Stokes equations, we can derive equations from the small perturbations, which can then be solved using linear techniques such as the eigenvalue analysis and perturbations methods. For instance, in asymptotic wave propagation, the press and velocity perturbations are small and linear, allowing us to use the simplified wave equation to describe the behavior of sound waves in a fluid. Similarly, when studying the stability of a fluid, for example in a pipe, linearization allows us to analyze how small disturbances grow or decay, helping us predict whether the flow will remain stable or transition to turbulence. To summarize, linearization in fluid mechanics allows us to simplify complex linear systems by approximating them as linear systems, making them easier to analyze and solve. By applying linear techniques to small perturbations in fluid flows, we can gain valuable insights into the behavior of fluid without the complexity of full nonlinear models. Linearization is essential in various fluid mechanics applications, from asymptotic wave propagation to fluid stability analysis.